Hello, ladies and gentlemen. Welcome to week 6 of distance learning chemistry. This week we are looking at organic chemistry and naming organic compounds. So today we're going to start with some notes and look at a brief overview of organic chemistry, what it is, and some different aspects of organic chemistry. So first of all, we want to start by answering the question, what is organic chemistry? And organic chemistry is a field of chemistry that deals with a specific element, in this case, carbon. Organic compounds are carbon-based compounds, but not all carbon compounds are organic, okay? So please keep that in mind. CO2 is not organic, and carbon monoxide, or CO, is also not organic. Carbon can do a lot of different things. We can build a lot of different structures and molecules with carbon. So it can bond with itself, as we'll see, and it can bond with a lot of other elements as well. A couple of basic shapes that will form out of these carbon compounds are rings, which are like circular or closed ends where the ends come around to touch, or forming chains that are linear and go across in a straight line. Pure carbon has different forms. So there's different types of carbon within carbon. So we have graphite, which is in pencil lead, and as you write with a pencil on paper, what you're doing is laying down these different layers that are stacked, as you see in the graphite picture. So those layers come out onto the paper, onto the surface of the paper, and leave the markings on your paper that are writing. On the right, we've got the structure of a diamond. So you can see slightly different. This is a network, as it's called. So this network goes out and attaches to multiple other carbon atoms, forming a very, very strong structure due to the network bonding pattern that it forms. We also have carbon nanotubes as another type or form of carbon, and these carbon nanotubes can be used for delivering a variety of substances in a variety of different means, methods, and locations, biologically speaking. And then we have Buckminster fullerene, or sometimes called buckyballs, which is 60 carbon atoms that are put together into a sphere. And these are also used for containing compounds or holding compounds in some cases, depending on the application. There's a lot of different applications for them. So just to give you an idea of what we're talking about with organic chemistry, we've got aspirin here on the screen as one example organic compound. You can see the ring shape here that we're talking about with the 6 carbons. So this is a 6 carbon ring with some branches off of it in a couple places. And then caffeine, you can also see, is a molecule that a lot of you are probably familiar with, but its structure is also a ring type structure. We've got a 6-sided ring with some nitrogen atoms, and then over here we've got a 5-sided ring with some nitrogen atoms as part of that 5-sided ring. Tylenol is acetaminophen, and acetaminophen is another ring type structure, as you see, with a branch off of the side here. And then one that we're familiar with flavoring, maybe an ice cream, milkshake, a whole lot of other places that you might find vanilla in. But the flavor of vanilla is one that's called for in a lot of kitchen recipes if you're baking in the kitchen. And you can see it's based off of a ring as well, and it's got a couple branches here and down here. And then the drug morphine, a narcotic, is a ring structure with some branches as well. Here you can see down on the lower left of the morphine structure, it's got a ring and then some other branches and groups that are attached to that morphine. And last of all, wintergreen, right? Like lifesavers or gum, for example, have wintergreen oil in them for flavoring. And this is based off of a ring-shaped structure, six-sided ring. And then it's got a couple of branches off of that six-sided ring to give the wintergreen flavor. Next, we want to look at what are called isomers. And isomers are a way that carbon atoms arrange themselves into compounds, and these arrangements can change. And these give us isomers. So even if the formulas are the same, we can have a different structure with the same formula. Okay, so these are what we call isomers. So we can have geometric isomers, which have the same formula, same shape, but the atoms are bonded in a different order. So there are also geometric isomers, and there are structural isomers. So within isomers, we can have two types. We can have geometric isomers and we can have structural isomers. A structural isomer is our second type, which has the same formula, shape, and the order are different. Okay, so shape and order are different, but they do have the same formula. So isomers for geometric, here's one example, right? With C2Br2H2, we've got the BRs both on the right-hand side, and then notice over here in this isomer of the same compound, it is different in that the BRs are now diagonal from each other rather than on the same side of the double bond. So we've got a double bond here in the middle with two lines. The BRs are on the right-hand side. On the second isomer, we've got the double bond, and the BRs are split onto opposite sides. So we call the isomer on the left, because they're on the same side of the double bond, both on the right, that these are cis isomers. If they cross over the double bond, like the one on the right has Br on the right and on the left of the double bond, this is called a trans isomer. So in this example, we have another isomer of platinum. We have cisplatin and transplatin. Cisplatin is a cancer drug that's used in fighting cancerous cells and tumors. Transplatin is not. Let's look at structural isomers now over here on the right. Structural isomers, both are C4H10. So the formulas are the same, being made up of 4 carbons and 10 hydrogen atoms attached to the 4 carbons. This gives us butane. We have, notice on the left-hand side here with butane, we have N-butane, which is linear or a straight line. And then on the right-hand side, we have what's called isobutane, where we took one of the C's off of the linear structure and put it on top in the central carbon, and that gives us what's called isobutane. So it's an isomer of the N-butane, or another form. They're put together differently, but they do have the same number of carbons and hydrogens making up both of those isomers. So you might hear the term hydrocarbon when scientists are talking about organic compounds, and hydrocarbons are simply carbon-based compounds that have hydrogen attached to them as well. So they're made up of those two elements, hydrogen and carbon, thus hydrocarbons. We can have saturated hydrocarbons, which have all single bonds, like our butane example on the last slide when we were looking at isomers. Those butane molecules had only single bonds. So we would say that's a saturated hydrocarbon for butane. You could also have unsaturated hydrocarbons. And for unsaturated hydrocarbons, you have at least one double or triple bond between carbons of that structure. So the C2H2Br2 example that we looked at, the cis-trans isomers, those would be unsaturated because both those structures had double bonds, and we were just looking at where the bromine atom was in relation to the double bond. So in naming hydrocarbons, we use this alk root word, and then depending on the bonds that are making up the hydrocarbon, if it's single bonds, the alk is going to be followed by a suffix ane, as noted down here on the bottom of the slide. So the ane denotes single bonds or saturated hydrocarbons. You might have a double bond, like we saw in the C2H2Br2, which is an ene or ene ending, indicating a double bond. So these would be alkenes. These are called unsaturated hydrocarbons. And then lastly, you might have a YNE ending called an alkyne. The YNE ending denotes a triple bond, which is also considered unsaturated. So let's look at some examples, and this will kind of lead us into where we want to head in our next lesson with naming hydrocarbons and practicing some naming independently on your own. So these are some prefixes, a list of prefixes for naming hydrocarbons. And we want to kind of dissect these and understand what is in a name or what the name means. Okay, so this first structure up here with three carbons is propane. Remember, we just talked about hydrocarbon names and the endings. So the ane ending for propane is indicating that propane has all single bonds between the carbons. And you can notice that with the structure. If you look at the structure, each carbon is linked with a single bond. Now, the prefix prop is what we want to look at on this slide. And prop, if you look over on the left-hand side here on our list, to the left, the prop prefix is the third one down. Notice we start with meth, eth, and then prop. So prop is a prefix for three carbons in this chain. So propane is telling us that there's three carbons that are linked together with single bonds only. Okay. Now for structure number 2, we have butene. Okay. And it's actually one butene, and we'll talk about the one in a minute. To look at this parent chain name, we have the but prefix. But is fourth from the top in our list. If you look at BUT, it's pronounced butte. So but is number 4, indicating 4 carbons in a chain. And then our suffix attached to but is an ene ending in this case. So with the ene ending, we're indicating a double bond, as we talked about with hydrocarbons on the previous slide. So the double bond ene is attached to the but to give us butene. Now the interesting thing is, and it makes sense when you stop to think about it, is when you have a double or a triple bond, you also need a number attached with that to tell the reader where in the chain is the double or the triple bond. So in this case, we have a chain of 4 carbons, right? And so it's counted off with little blue numbers on the carbons, as you can see here on the screen. And those little blue numbers counting off the carbons help us with the bute, but they also help us in telling the reader where the double bond in butene is. Because if we just say butene, the reader would ask the question, well, where's the double bond in the butene? So we use numbers to indicate the location of these double or triple bonds, as we'll look at in the next example. So 1-butene is telling us, as we look at the structure, that the double bond is between carbon 1 and carbon 2. It immediately follows carbon 1. And we want to count these structures in such a way that when we number the multiple bond, whether it's a double bond or a triple bond, we want to count these in a way that's going to give the multiple bond the lowest number value. So this is 1-butene. Let's move on to the third example down here at the bottom. Notice we have 6 carbons. We've got 1, 2, 3, 4, 5, 6. So this is hex. If we count down in our list from the top, we talked about bute was 4, pent would be 5, and hex would be 6. So hex, being 6 carbons, has an En or a YNE ending in this case, and the YNE ending on the hex, called hexine, is telling us that there's a triple bond. Okay, so as we talked about with the previous example, the next question then, if it is hexine, and we know that we have a triple bond, where is the triple bond? Okay, so in this case, we need to count the carbons and find out where the triple bond is, keeping in mind, as we mentioned a minute ago, that these multiple bonds have to be counted with the lowest possible numbering system. In this case, because the triple bond is in the middle, it doesn't matter if we count from the left end or the right end, we're still going to come out with the number 3 no matter which direction we count from. And you can pause the video and count on your screen and test that theory for yourself. But this is going to give us 3 for the multiple bond. So the location being at carbon number 3 gives this compound the name 3-hexine. 3-hexine. 3 for the location of the triple bond, which gives the YNE ending, and hex telling us that it's 6 carbons in length. So when we get to something like this, this is what is called a branched hydrocarbon. Okay, and a branched hydrocarbon, we need to find the longest continuous chain of carbon atoms linked together. So if we count on this one, we can count a couple directions, but we're going to get the longest carbon chain starting up here, counting down, over, and then at the bolded carbon, continuing down. That'll give us the longest continuous carbon chain. So if we do that, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons in length. So 9 carbons in length that are all linked by single bonds is going to be named nonane. So here, if you look at nonane, that's the 9-carbon hydrocarbon that we would consider the main backbone or structure of this substance. We then have some other parts that are preceding the nonane. So we're going to talk about those with these branched hydrocarbons. Okay, so the 4-ethyl, 4,6-dimethyl, we need to number these like we said before so that these are at the smallest possible number combination. So if we count up from the bottom, this carbon here is going to be carbon 4, which has the 2-carbon ethyl branch off of it. And if you look at our list a slide or two ago, you can see that list of roots for carbon names. And ethyl is the root for a 2-carbon branch. So at carbon 4, we have this ethyl group up top off of this bold carbon. And then we also have what's called a methyl group here to the right on carbon number 4. If we keep going to carbon 5 and 6, where we turn and go up, this methyl group is also attached to carbon number 6. So because we have one at carbon 4 and one at carbon 6, notice that we put 4, 6, because there's one at carbon 4 and one at carbon 6. And then because there's 2 of those, we use this small prefix after the 6, which is di. Di, of course, meaning 2. So there are 2 methyl groups, one at carbon 4 and one at carbon 6. And then the ethyl group is named for its branch, which is off of carbon 4. That gives us 4-ethyl, 4,6-dimethyl nonane. Let's go to the next example here. This next example, we have a 7-carbon chain. If you look at the roots part of this molecule's name, heptane, hept is referring to 7 carbons, and then the ane ending is telling us that they're all singly bonded together. So heptane is 7 carbons. We then have some branches. We have some small methyl branches or CH3 branches at carbon 2, 3, and then we also have the ethyl at carbon 2. Okay, so this would be carbon 2. With our ethyl group. Okay, so 2-ethyl, 2,2,3 trimethyl. Heptane. All right, let's move on to functional groups. In our functional groups, if you take off a hydrogen off of a hydrocarbon chain, you can add something new called a functional group. It's a group of atoms or a single atom to change the properties of the chemical. So here is a list of the functional groups, and you can pause the video and read through these as you want to, but we're going to be working with some of these functional groups perhaps on our naming assignment. And then we need to finish up with polymers, which are large molecules made of many small molecules joined together. So a lot of plastics that you might be familiar with are polymers. And the individual pieces that link together to form these polymers are called monomers, right? So mono meaning one, poly meaning many. So monomers are 1 units or single units that get linked together to make these polymers, or multiple linked units together. So in one example, you might have ethylene, which gets linked together in a polymerization reaction to form this polymer called polyethylene, which is a very common plastic. So that's where we are going to end for today. And hopefully that gives you a good overview. We'll look a little bit more at naming in lesson 2. But for now, I'll leave you to answer the lecture questions for organic chemistry in Google Classroom. So you can jump on over there, find the lecture questions, type in your responses using the notes and this video, and send those to me in Google Classroom. If you have questions, reach out via reminder, email, and I'll get back to you. Have a great day.